Perfect. So hi everyone, my name is Ankush and I'm a researcher at University of Minnesota. And today I'm going to talk about our work on integrating physical principles into machine learning algorithms for hydrology. And this work is being done jointly by a number of researchers from both computer science as well as hydrology from University of Minnesota and Penn State University. Okay, so in the last few talks, we have heard a lot about stream flow and how important how important it is to estimate that or forecast that accurately. And there are a number of physical models that are being used to tackle this problem, but they face numerous challenges, and calibrating these models is one of the biggest challenges. And in a number of cases, we don't understand all the processes completely, which makes it challenging algorithms. And similarly, just using data alone might not solve our problem because it would require a lot amount of data to capture the complex relationships between our weather inputs and our output variables, which is stream flow in this case. And again, even if we have a lot of data, we might not get physically consistent results, which is also important in our application. Okay, so our goal basically is to see how can we bring these two things together, or the complementary aspects of these two aspects. Okay, so if we just quickly look at this problem from a machine learning perspective, a very reasonable thing to do would be to use a machine learning architecture which is time aware, and it takes weather inputs and then produces output variable, which is stream flow in our case. So very popular models would be using LSTMs or GRUs, and you have seen quite a bit of them in the past few talks. So this is just looking at this problem from a machine learning perspective. But if we look at this problem from a physics perspective, we can see that there's a very complex relationship between our weather inputs and stream flow. So here in this slide, I'm showing you a graphical view of the water cycle. And we can see there are a number of processes that are directly and indirectly related with stream flow. And another interesting property of our system is that it has a memory, which is basically the amount of water stored in the system at any given time. Basically, that water could be stored in the soil as soil water or soil moisture, or it could be stored as snow. And the amount of this water has a big impact on how these different processes respond to our inputs. For example, for the same amount of rainfall, we can have very different surface runoff depending on how much water is already present in the soil. Similarly, on a very hot day, the amount of water that will become available by snow melt will depend on how much snow is already there on the ground. So knowing these storage variables can help us in doing a better job in estimating stream flow. So from a machine learning perspective, these two states are interesting. Okay, so basically our goal in this project right now is to evaluate the utility of incorporating these states and fluxes directly into the machine learning framework. Would they bring value? Would that reduce the complexity of our problem? That's what we are trying to explore in this project. So what are the different ways in which we can bring these states and fluxes into our Again, the architecture on the left is the basic architecture that I showed before, that uses no physics information and directly tries to model stream flow from weather inputs. And the architecture in the middle is trying to show that we can bring in these extra variables as inputs to our system. For example, in the previous talk, Chris showed that he used precipitation together with evapotranspiration to drive his LSTM model. So this is one way in which we can do it, but in a lot of situations, we will not have access to these derived variables directly from reanalysis data sets. So a more general approach that we are exploring is to model these intermediate states and fluxes from our core weather variables, and then feed that to our final process estimating stream flow. So for example, in this architecture, we are using weather inputs to first learn ET, soil water, snowpack with different LSTMs, so that they can all capture different temporal scales and things like that. And then the output of these individual modules are fed to the final module, which is trying to estimate stream flow. So the benefit of this is that it reduces the complexity from one module to capture all of these complex processes together. And once we bring these things into these variables into the architecture, we can impose another layer of constraint, which is basically using physics-based loss functions to constrain these individual modules to adhere to our conservation of mass principles, and we heard about those in previous talks as well. So this is basically setting up the roadmap of what we are trying to evaluate or assess in this work. But in this talk, I'm going to just show a small set of results based on a very simple, relatively simple variation of this architecture, where we are not going to use physics-based loss right now, and then also we are going to model these individual states separately, and then pass that as input to our final module, which is trying to estimate stream flow. So in some sense, instead of learning them simultaneously, we're just learning them separately and seeing how adding these modules will impact our results. Again, and the reason why we focused only on soil, water, and snowpack is because these are the storage variables, and we wanted to understand their value in improving the performance. All right. So to drive all our evaluation, currently we are using a 200-year simulation that we generated from SWAT model, which is a hydrology model, and this was done for a watershed in southeast Minnesota. So basically, to drive the simulation, we need inputs, and so the inputs were created from a weather generator that is part of this SWAT module. And it basically creates these inputs, which is precipitation, temperature, basically min and max for that day, humidity, wind speed, and solar radiation. Again, this is a daily scale model. And I also want to highlight here that in all the few results that I'm going to show today are done on the simulation. We don't have results for real data right now, and we are working towards that. So when you create these inputs, you pass them to the SWAT model, physical model, and it generates stream flow and all the other different intermediate states and fluxes that it calculates. So our goal right now is to see how can we emulate SWAT effectively by bringing some of these physical concepts. So again, we're trying to emulate right now. We're not trying to do experiments on real world data. Okay, for a very quick overview of the experimental setting, we are going to use the first 120 years for training and last 80 years for testing. And we chose our sequence length for LSTM to be 180 days, which is roughly half a year. Again, we did a lot of optimization in the back. We tried a week, 1 month, 2 months, and 1 year, and things like that. And we picked half a year because it gave reasonable results. And then we decided the hidden features for LSTM to be 28 in our case. Again, so that's just the basic overview of the experimental setup. Okay, so now let's look at the results. So on this slide, we have calculated two different error metrics. One is RMSE that everybody's familiar with, and NSE, which is a very widely used metric in hydrology, which is trying to basically compare the estimates from a model, from a machine learning model, with a very baseline approach, which would be taking the mean of your observations as your potential model. So how better is a machine learning model than the baseline? So that's what NSE tries to capture. So now let's look at the results one by one. So the first row, it provides the, again, so we have two columns. One is for training RMSE for the first 120 years, and then test RMSE for the last 80 years. And the numbers in the bracket show you the standard deviation across 5 different random runs that we did for each of these scenarios. Okay, so the first row gives us the information when we just use physics, where we are not using any physics. So basically, start from weather input, have one LSTM that tries to capture stream flow. So we get an RMSE of 0.78. And then the second row gives the results when we added an intermediate module that tries to capture soil water. So basically, the goal of that module is to predict soil water at any given time, and then that becomes the input to our stream flow module. So as you can see that as soon as we add this module, the RMSE goes down to 0.56, and similar trend can be seen in the NSE value as well. So this kind of gives us a quantitative view of the utility of adding those intermediate states as part of the architecture. And then we added another module that tries to capture snowpack at any given time, and that further reduced the RMSE. So that kind of tells us that there is some value in bringing these concepts into the architecture itself. Now the time series on the bottom kind of shows you the result for one of the testing years. So here, the black diamonds that you can see are the stream flow from the SWAT simulation, because our goal right now is to emulate SWAT. So what we want is our machine learning algorithm to be as close as possible to these black diamonds. And the green circles are basically predictions from a no physics based model. And the red line is from a model that has both soil, water, and snow as intermediate states being modeled. So as you can see that the red line is much closer to black diamonds. If you look in the beginning of the year here, it's matching the peaks more accurately than not using those intermediate states. And you can also see that it removes the spurious low stream flow values from the predictions as well. So this kind of gives us both quantitative and visual validation that adding these states is bringing value to our machine learning architecture. All right, so now let's dig a little bit deeper into these storage variables, as I call them. To just highlight it for machine learning audience, that there's very interesting patterns to these memories. For example, soil water, it doesn't start from 0 for any given sample. Like if you think from an NLP application, when you're trying to work with a sentence, in the beginning you have no memory, and as you see more and more of the sentence, you start building your memory. But in our case, if you take any 6-month period in this time series that I'm showing you, which is basically 10 years of soil water, you can see that it's not going to start from 0. So basically what we observed is that giving information about the initial state, value of soil water helps in modeling the soil water itself. Again, I'm not going into the details of how to do that, but that's one of the things that I want to highlight. So basically, we need to think of different ways in which we can model states rather than just using plain LSTM. And similarly, if we look at snowpack as a state variable, it resets after every season in almost all geographies. And then, within winter season, it could drastically drop down to 0 as well. So it has that property of accumulation and dissipation, but it happens at much faster than soil water. So very different temporal scales. But another thing to note about this storage variable is that it has very simple relationships with temperature. So we could reduce the complexity of modeling this variable by adding some of those physics-aware inputs or derived inputs. So these are some of the insights that we could bring in to model these storage variables. Now the final slide is about, so what we did is we tried to compare our results from an LSTM with our physical variables to see if there is any physical meaning. So in this case, what we did is we just used our plain LSTM, which has a single module that takes inputs and produces stream flow. And then we compared the hidden features, like we have 28 possible hidden features, with some of the known quantities. In this case, you can see the top figure is comparing hidden feature number 23 with Snowpack. And you can see that it has a reasonable agreement with Snowpack, which is very interesting that even with no information about Snowpack, a hidden feature is trying to emulate Snowpack, which is a very promising sign from a machine learning perspective. And similarly, if you look at soil water, we see hidden feature number 4 shows a reasonable agreement with soil water. So here we are looking at 1 year's worth of data. So again, this just to kind of another way to validate that yes, these two states are important in doing a good job in estimating stream flow, and a basic LSTM is automatically trying to capture this. So our goal basically going forward is to come up with different ways in which we can model these states and memories by changing the architecture or bringing new ideas into the framework. So some of the other ideas that we are planning to pursue is so right now I told you that we individually trained LSTM for Snowpack and soil water, and then fed the output of that input to the final module. But we could do that, we could train all of these simultaneously in a multitask learning framework. So we would explore that going forward. Again, we are going to add a mass balance equation to further constrain the model. And then the main important thing is to evaluate this strategy on real world data set as well. And finally, right now we are focused only on one watershed. Our goal is to analyze this across different watersheds, and we saw some very exciting data sets like camels, which would be a very good way to test some of these ideas. So that's all from my side. Thank you for your attention, and happy to take some questions.
Thank you, Ankush. We have right now just one question, and that is, how will you apply this framework on real data? I guess you will need observations on all state variables.
So yes, so the idea is basically use this as a pre-training mechanism. So in the previous talk, we heard about like transfer learning, where you learn a model in one setting and then you apply on the other. So you could do the similar strategy with using a simulation as a pre-training mechanism, and then you test it or fine-tune it on real-world data. So what we are going to do is, while we are pre-training, we will have access to those storage variables to learn those modules. But while testing or while using real data, we would be able to only fine-tune the stream flow module, but we could still apply the physics-based constraints on the other modules, which will indirectly impact our final result. So that's how it's going to play out with real world data.
We got some more questions. That's nice. Could you explain more about how you get the initial value of the soil moisture? Where can you learn?
Yes.
Yeah.
So basically, this was one of the ideas that we tried. Basically, what we did is, while training, we try to simulate machine learning like a physical model that you would run. For example, when you start simulating from a physics-based model, you give it initial conditions like, okay, I'm starting it on day 1. This is the initial amount of soil water. It's already present in the soil, and then it simulates from there, right? So we kind of tried to do the same thing, where while training, we provided for example, we took the sequence length to be 180, which is half a year. So for any given sample, while training, we provided the soil water value on day 1 of that sample, and then just copied it for the rest of the sample. So basically what we are telling machine learning is that this is the value that's present today. Now simulate soil water from here. So that's what we did, and we saw so that the improvement that we saw from 0.78 to 0.56 was not happening if we don't add that concept. So that was during training, and then during testing, we just let the prediction of the previous sample served as the initial value for the next, and it worked fine. Again, that's just one of the ideas. There could be other ways in which we could bring that.
With that same question, there was a question about where they can learn more about this. Is there a paper or code? And I think that you'll probably say that there's a paper that will come out eventually, right?
Yes, it is. It will come out soon, yes.
Yeah, okay. Another one, since we do have time, what if the observed state variable observations do not obey conservation of mass? And I know that you haven't looked at the observed data in this analysis that you've been doing here, but I think that might be something you might project ahead to think about this.
Yeah, that's an interesting question. Again, as somebody asked that question previously, that you don't have observations of those intermediate state in real world. So we may not be able to even tell whether in real world it is being followed or not. We would just apply that constraint because we know by physics it should follow. So I think that's the best way I could answer that question, that what if it doesn't follow physics. Yeah.
Okay, and then one more question, that is, if the simulated soil water has large bias, and quote in parentheses, any validation of this, how would this affect your prediction of stream flow?
Yes. So we, yeah, I think what I'm trying to, what I'm understanding from the question is that a poor modeling of soil water can negatively impact our performance in modeling stream flow. It definitely can happen, but we haven't analyzed it that thoroughly yet. But what we saw was in our current experiment, if we use just 7 inputs without this initial value idea, we were not getting any improvement from 0.78 to 0.56. So that kind of gives you an indirect answer that a simple modeling of soil water was not enough to get that performance improvement.
Okay. Well, those are the questions we got. Thank you very much for the great presentation, and maybe there'll be more questions in the general question period.